Welcome to Paradox Lab. The cosmic curtain call, look up at the night sky. What you see is a fleeting, glorious anomaly. We live in a golden age of light, an epoch known to astrophysicists as the Stelliferous era. It is a time when cosmic nurseries are bursting with newborn stars, when galaxies burn with the fierce brilliance of billions of suns, and when the chemical building blocks of life are forged in stellar furnaces. We take this light for granted. We perceive the universe as a permanent monument of fire and energy, a static canvas that has always been and will always be, but it isn't. To understand the universe, you must understand that it is governed by an inescapable law, the second law of thermodynamics. Entropy, the measure of chaos and disorder, is always increasing. Energy is constantly spreading out, moving from highly concentrated, useful states, like the fiery core of a star, into scattered, useless heat drifting through the void. In the grand timeline of the cosmos, this era of light is nothing more than a spark in a boundless midnight. Every star you see, every galaxy that anchors our reality, is running on a finite supply of fuel. Hydrogen is being spent, gravity is constantly demanding payment, and the cosmic clock is ticking toward an inevitability that defies human comprehension. For decades, scientists debated how the universe would end. Would gravity eventually overpower the expansion of space, pulling everything back together in a catastrophic big crunch? Or would the fabric of space-time tear itself apart in a big rip? Today, the consensus points to a quieter, more haunting fate, the big freeze, or heat death. Imagine a time when the universe runs out of gas. A time when the last stellar nursery dries up, when the most resilient stars exhaust their final reserves, and the cosmos plunges into absolute, irrevocable darkness. What happens when the last star turns off? What takes its place in a universe that has forgotten the very concept of light? Welcome to the deepest, darkest chapters of our future. Today, we are going to leave behind the familiar cosmos of planets and starlight. We are embarking on a journey across unimaginable spans of time, from the final agonizing gasps of the last red dwarf to the rise of the ultimate masters of the dark universe, black holes. This is not science fiction. This is the ultimate destiny of our universe, calculated by modern physics. Strap in. We are about to witness the end of time itself, the twilight of the Stelliferous era. To understand the black hole era, we must first watch the old world die. The transition from our current universe to the universe of darkness doesn't happen overnight. It takes roughly 100 trillion years. By the year 1 trillion, the universe is already unrecognizable. Due to the accelerated expansion driven by dark energy, the space between galaxies is stretching faster than the speed of light. Because of this, all galaxies outside of our local supercluster have slipped beyond our cosmic horizon. The light from those distant galaxies can no longer reach us. If human beings, or any conscious observers, were alive in this distant future, their night sky would be profoundly empty. It would reveal only one massive, merged supergalaxy, the chaotic result of our Milky Way colliding with the Andromeda galaxy. To these future observers, this single island of stars would appear to be the entire universe. They would have no way of knowing that billions of other galaxies ever existed. Within this lonely supergalaxy, the fuel gauge is dropping to zero. The giant interstellar clouds of dust and hydrogen gas, the cosmic nurseries that gave birth to stars like our sun, are entirely depleted. As the gas clouds exhaust their hydrogen, the universe experiences a great dying. Massive blue stars disappear first. These stellar giants, some weighing 50 to 100 times the mass of our sun, burn with incredible ferocity, but their massive gravity forces them to consume their fuel at a reckless pace. They burn bright and die young, lasting only a few million years before detonating in spectacular supernovas. Then go the yellow suns, the stable, medium-sized stars like our own. Our sun has a lifespan of about 10 billion years. When its core runs out of hydrogen, it will swell into a massive red giant, swallowing the inner planets, before shedding its outer layers and leaving behind a glowing, dead core. One by one, the yellow stars blink out. Eventually, the universe is populated entirely by one single class of star, the red dwarf. The last stars in the universe, red dwarfs, are the ultimate survivalists of the cosmos. they possess only a small fraction of the Sun's mass, sometimes as little as 8%. Because they are so small, their internal gravity is much weaker, and their nuclear furnaces burn at a much cooler temperature. They do not burn their hydrogen violently. They sip it at an agonizingly slow pace, but their true secret to longevity lies in their internal anatomy. Unlike our Sun, which traps its helium ash in its core and can only fuse the hydrogen located in its very center, a red dwarf is fully convective. It operates like a boiling pot of water. It constantly circulates its entire volume, moving hot helium up to the surface and pulling fresh, unburned hydrogen down into the core. This perfect internal circulation allows a red dwarf to consume nearly 100% of its hydrogen fuel. Because of this extreme efficiency, a red dwarf can live for up to 10 trillion or even 17 trillion years. Trillions of years from now, long after the Earth is gone, these tiny, dim red stars will be the only remaining sources of warmth in a freezing universe. Any remaining civilizations will have no choice but to huddle around them, building their final megastructures in the dim crimson light. But even these ultra-efficient stellar engines must eventually succumb to the laws of physics. As a red dwarf reaches the end of its incredibly long life, it begins to run out of hydrogen. As the fuel depletes, the star's internal dynamics change. Paradoxically, as it starves, it grows hotter. The star transitions from a dull red to a radiant yellow, and finally to a brilliant, blinding white blue. It enters a theoretical phase known as a blue dwarf. Because the universe is currently only 13.8 billion years old, it is far too young for a single blue dwarf to exist yet. We can only predict them through mathematical models. For a few million years, the blue dwarf burns with a brief, frantic intensity screaming against the dying of the light. But it is a false dawn. Once the last microscopic drops of hydrogen are fused into helium, the nuclear fire goes out completely. Without the outward pressure of nuclear fusion to fight against the inward crush of gravity, the blue dwarf collapses into a dense, planet-sized ember, a helium white dwarf. By the year 100 trillion, the final red dwarf in the cosmos flares blue and then fades away. The Stelliferous era is officially over. The universe has run out of starfire. The Degenerate era and the cosmic graveyard welcome to the Degenerate era. The cosmos is no longer an ocean of light. It is a sprawling, frozen graveyard of stellar remnants. The primary residents of this era are degenerate objects, corpses held up not by nuclear fusion, but by the bizarre and unyielding laws of quantum mechanics. We are talking about white dwarfs, neutron stars, and brown dwarfs. When a star dies and becomes a white dwarf, it packs half the mass of our Sun into a sphere no larger than the Earth. The gravitational pressure is so intense that standard atoms are crushed. The only thing preventing the white dwarf from collapsing into a black hole is a quantum phenomenon called electron degeneracy pressure. The laws of quantum mechanics dictate that no two electrons can occupy the same exact state at the same time. When gravity tries to squeeze them too closely together, the electrons violently push back, locking the star into a rigid, ultra-dense structure. A single teaspoon of white dwarf matter would weigh as much as a commercial airplane on Earth. Without a source of internal heat, these white dwarfs spend the next quadrillion years slowly radiating their leftover thermal energy into the freezing vacuum of space. As they cool, their interiors undergo a bizarre transformation. The carbon and oxygen atoms within them lock into a highly organized crystalline lattice. The star literally turns into a gigantic cosmic diamond, gradually, over timescales that make the age of our current universe look like a passing second. These diamond stars transition from white to yellow to red, and finally into cold, dark lumps of degenerate matter, black dwarfs. Black dwarfs are the ultimate ghosts of astrophysics. They emit absolutely no light, no heat, no radiation. They are invisible, silent monoliths drifting through an unlit void. Every dead planet that once orbited a sun is now locked in a permanent sub-zero freeze, circling a pitch-black star. Alongside the black dwarfs are the neutron stars, the collapsed cores of the ancient giant stars. These objects are even more extreme. They are so dense that electrons and protons have been violently crushed together to form a solid sphere of pure neutrons. A neutron star the size of a small city possesses the gravitational pull of 1,000,000 Earths. In the Degenerate era, these silent, spinning heavyweights drift aimlessly through the dark. Occasionally, the silence is broken. Trillions of years can pass with absolutely nothing happening. But the cosmos is vast, and eventually, the random paths of these dark objects intersect. If two dead brown dwarfs, objects that never had enough mass to ignite into stars, happen to collide in the dark, their combined mass can momentarily exceed the threshold for nuclear fusion. For a few brief, glorious billion years, a transient, accidental star lights up the dark, casting an eerie glow over the ruins of old galaxies. It is a brief resurrection, a zombie star in a universe of ghosts. But these accidental stars are rare anomalies. The true, fundamental question of the Degenerate era is far more deeply tied to the nature of reality itself. Is matter actually stable? The dissolution of matter. We are taught that matter cannot be created or destroyed, only changed in form. But modern physics suggests a terrifying caveat. Many grand unified theories, the complex frameworks that attempt to merge the forces of nature into a single mathematical equation, predict that the fundamental building block of all atomic matter, the proton, is not immortal. Protons are incredibly stable, which is why everything around us exists. But they are theorized to have a half-life. It is an unimaginably long half-life, roughly 10 to the 34th power to 10 to the 37th power years. If protons are indeed unstable, then the universe is about to experience a slow architectural dissolution. Inside every black dwarf, every wandering neutron star, every frozen asteroid, and every dead planet, protons begin to decay. As a proton breaks down, it transforms into a positron and a neutral pion. These subatomic fragments almost instantly annihilate each other, turning into a microscopic flash of pure gamma-ray energy. Imagine standing on the surface of a frozen, dead Earth in this era. The ground beneath your feet would faintly glow as, atom by atom, the planet simply melts away into radiation. Over vast stretches of time, solid matter loses its integrity. The massive diamond stars and the unbreakable neutron cores turn into vapor. By the year 10 to the 40th power, every physical object, every rock, and every piece of dust has dissolved into a thin mist of fundamental particles. But what if the grand unified theories are wrong? What if the proton does not decay? If protons are immortal, the Degenerate era lasts much, much longer, and it leads to something even stranger. The Iron Star era, over 10 to the 1500th power years. A process called quantum tunneling allows atoms within black dwarfs to spontaneously fuse at room temperature. It is a process so slow it is almost imperceptible. But over an eternity, every atom in every star and planet will fuse until it reaches the most stable element in the universe, iron. The cosmos would be filled with massive, cold, metallic spheres of pure iron. But eventually, even these iron stars will meet their end. Through gravitational radiation and quantum mechanics, they will ultimately collapse into themselves. Whether through proton decay or quantum collapse, the end result is exactly the same. Solid matter is erased from the universe, except for the matter that was swallowed by something much larger and much darker. The dawn of the black hole era with the erasure of ordinary matter, the universe enters its fourth major phase, the black hole era. For the past unimaginable stretches of time, black holes have been patiently waiting, while stars lived and died, while galaxies dissolved, and while the very atoms of the universe rotted away. Black holes did nothing but feed and grow. Now, they are the undisputed monarchs of the cosmos. Every other physical structure has vanished. The universe is now an unfathomable expanse of near-perfect vacuum, populated solely by scattered, isolated black holes of varying sizes. There are the stellar mass black holes, the ancient remnants of the universe's earliest, most massive stars. There are intermediate black holes, the elusive predators born from runaway stellar collisions. And then there are the supermassive black holes. These ancient titans, weighing as much as tens of billions of suns, once sat at the radiant hearts of galaxies. Now, they sit entirely alone in the void, In the early parts of this era, the remnants of old galactic cores undergo a process called dynamical friction. Black holes slowly sink toward the centers of their combined gravity wells, finding each other in the dark. When two supermassive black holes merge, they emit a cataclysmic burst of gravitational radiation. These invisible ripples warp the very fabric of space and time across trillions of light years. In the black hole era, these violent mergers are the only major events taking place in the entire universe. They are the final, thunderous announcements of cosmic structure. What is reality like during this era? It is an era of absolute isolation. The expansion of the universe has long since stretched the distance between these monsters to impossible lengths. A single supermassive black hole might sit alone in a volume of space far larger than our entire observable universe today. If you were an indestructible observer standing outside the event horizon of one of these titans, you would see absolutely nothing. There are no stars to warp into rings of light, no gas clouds to form a glowing accretion disk. The sky is a flawless, perfect canvas of black. The only thing that exists in your reality is the edge of the abyss, a spherical boundary where space and time simply drop out of existence. When a black hole is the only thing left in existence, it becomes the sole defining feature of physics. In the cold dark of the far future, most of these black holes are spinning rapidly. They are dynamic objects known as Kerr black holes. The mathematics of a Kerr black hole, dictated by Einstein's field equations, reveal a twisted reality. As the giant black hole spins, it drags the very fabric of space around with it, like a spoon stirring thick honey. This creates a terrifying region outside the event horizon known as the ergosphere. In this zone, it is physically impossible to stand still. Space itself is moving faster than the speed of light. Cross the threshold of the event horizon, and the laws of nature break down completely. Inside the black hole, the roles of space and time are inverted. Time becomes a spatial direction, pointing inexorably inward toward the singularity at the center. You cannot turn around and escape a black hole for the exact same reason you cannot turn around and travel backward into yesterday. The singularity is not a place. It is a fixed event in your future. Because of this terrifying stability, it once seemed that black holes would be the permanent, eternal end state of the universe. It was believed that once everything fell into a black hole, the story of the cosmos was over. A black hole was considered the ultimate lockbox from which nothing, not even information, could ever escape. But in 1974, a brilliant young physicist named Stephen Hawking discovered a loophole in the laws of absolute darkness. A loophole that guaranteed that even these immortal gods of gravity must eventually die. Hawking radiation and the cosmic evaporation. To understand how a black hole dies, we have to look much closer than the naked eye can see, down to the microscopic, shifting quantum foam that defines the vacuum of empty space. We tend to think of a vacuum as completely empty, but according to quantum field theory, empty space is a roiling, chaotic ocean of energy. In this ocean, pairs of virtual particles, a particle and its exact antiparticle, are constantly popping into existence out of nothingness. Normally, these particles find each other an instant later, annihilate, and return their borrowed energy to the universe. They exist on borrowed time, governed by the strict rules of Heisenberg's uncertainty principle. But what happens when this quantum dance takes place precisely on the geometric edge of a black hole's event horizon? Right at the threshold, the extreme gravity of the black hole can separate the particle twins before they have a chance to annihilate. One particle falls past the point of no return, sinking down into the black hole. The other particle, suddenly lacking a partner to destroy itself with, escapes into the vast emptiness of space as a real, tangible unit of radiation. Here is the twist. The universe demands that energy must be conserved. Because the escaping particle takes positive energy away into the universe, the particle that fell into the black hole must possess negative energy relative to an outside observer. When a black hole absorbs a negative energy particle, it doesn't grow. It loses a microscopic fraction of its mass. This steady stream of escaping particles is what we call Hawking radiation. The mathematics behind this process reveal a strange relationship. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. This means that the larger a black hole is, the colder it is. In our current era, supermassive black holes are incredibly cold, millions of times colder than the ambient temperature of space. Because they absorb more ambient heat from the cosmic microwave background than they emit via Hawking radiation, they are currently growing, not shrinking. But in the deep future of the black hole era, the universe expands so much that the cosmic background radiation cools to absolute zero. The environment of space becomes utterly freezing, finally dropping below the temperature of the black holes themselves. And so, the balance shifts. The black holes begin to bleed their mass into the void. The great evaporation begins. The process is agonizingly slow. A stellar mass black hole, weighing a few times more than our sun, takes about 10 to the 67th power years to evaporate completely. But a gargantuan supermassive black hole at the center of a former galaxy will endure for 10 to the 100th power years. This number, a 1 followed by 100 zeros, is known as a Googol. To put a Googol of years into perspective, imagine a solid mountain of diamond the size of the entire Milky Way galaxy. Now imagine a single bird flying past once every trillion years, brushing its wing against the diamond. The time it would take for the bird's wing to wear the entire mountain down to nothing is a microscopic fraction of a single Googol. It is a span of time that reduces the entire 8 billion year history of our universe to an unnoticeable microsecond. Yet, as time crawls endlessly forward, mass continues to bleed away. And because of the inverse relationship between mass and temperature, a terrifying feedback loop occurs. As a black hole loses mass, its temperature goes up. As its temperature goes up, it radiates energy at a faster pace. As it radiates faster, it loses mass even quicker. It is a runaway train of quantum evaporation. In its final moments, the black hole sheds its dark cloak entirely. It shrinks down from the size of a solar system to the size of a planet to the size of a mountain. As it shrinks, it glows red, then blindingly white-hot. During its final second of existence, it releases its remaining mass in a spectacular, violent flash of high-energy gamma rays and exotic particles. It is a cosmic explosion equivalent to billions of thermonuclear weapons detonating simultaneously in a single point of space. For one brief millisecond, the dark universe is flooded with brilliant light. One by one, across the unimaginable desert of time, the black holes of the universe go off like silent fireworks. The small ones die first, followed by the mid-sized predators. Finally, the ancient supermassive titans reach their expiration dates. Around the year 1 Googol, the final, largest black hole in the universe reaches its critical threshold. It heats up, flashes violently in the eternal night, and explodes into the vacuum. With that final explosion, the black hole era comes to an end. The last macrostructures in the universe are gone. Gravity has been defeated. The end of time. The dark era, what lies beyond the final explosion. We have arrived at the ultimate final phase of our cosmic timeline. The dark era. The universe is now entirely empty. Every star has burned out, every planet has dissolved, and every single black hole has evaporated. All that remains is an incredibly dilute soup of subatomic particles, photons, neutrinos, and a few stray electrons and positrons drifting blindly through an ever-expanding, infinite void. Space continues to expand, stretching the distance between these surviving particles to incomprehensible lengths. In this era, the distance between two single electrons might be larger than the size of our entire observable universe today. Very, very occasionally, over stretches of time that dwarf even the black hole era, an electron and a positron will find each other in the dark, bound by their opposite electrical charges. They will form a bizarre macro-scale atom called Positronium. Because space has expanded so vastly, these two particles will orbit each other across distances wider than galaxies, moving at a pace so slow it borders on complete stillness. Over periods of 10 to the 141st power years, their orbit will slowly, inevitably decay. Inch by cosmic inch, they spiral inward. Finally, after an eternity of falling, they touch. The electron and the positron annihilate each other, releasing a tiny, faint flash of energy, just a few weak photons of light drifting into the endless dark. After that, this is the ultimate fate of our universe. Heat death. It is the state of maximum entropy, the absolute victory of the second law of thermodynamics. All energy is completely and evenly distributed throughout the infinite expanse of space. Because there are no temperature differences, no work can be performed, no engines can run, no biology can exist, no information can be processed. Everything that can happen has happened. The universe has finally run out of events. When nothing happens, and nothing can ever happen again, does time even exist? We measure time by change, the ticking of a clock, the orbit of a planet, the beating of a heart. Without a clock to measure it, without a chemical reaction to mark it, and without an observer to experience it, the very concept of time breaks down. The arrow of time loses its direction. The universe becomes a static, eternal monument to nothingness. It has reached its final permanent state of absolute rest. The comfort of the Sparket is easy to look across these unimaginable timescales and feel a crushing weight in your chest. It is easy to succumb to a sense of profound existential nihilism. It is terrifying to realize that everything we build, everything we love, every memory of human civilization, every masterpiece of art, and even the burning stars themselves are just a temporary, fleeting anomaly. A momentary glitch in a universe that is destined for absolute, infinite darkness. But there is another way to look at this. The fact that our universe will eventually fade into a cold, dark void does not rob our existence of meaning. In fact, it does the exact opposite. It makes the present moment infinitely more precious. We are incredibly fortunate to live right now. We exist during the brief, glorious morning of the cosmic day. Out of the infinite stretches of time where the universe is dead, cold, and empty, we happen to be alive during the incredibly narrow window when the cosmos is hospitable. We live in a time when the universe is alive with light, when gravity can pull dust into warm planets, when liquid water can flow into oceans, and when matter can organize itself into complex, conscious beings capable of looking up at the sky and asking questions about its own destiny. You are not just a passive observer of the cosmos, staring out at something separate from yourself. You are made of the ash of dead stars. You are the universe. You are a way for the cosmos to know itself, to feel, to fear, and to wonder. We are the thinking, feeling fragments of a stellar generation that will one day become the foundation of the black hole era. We are the spark before the dark. So the next time you step outside, look up at the stars. Appreciate their immense, ancient light. Marvel at the sheer unlikelihood of your own existence in this fragile, burning era. Do not fear the darkness that is to come, but celebrate the light that is here right now. Because we are living in the golden hour of creation, and the night is a long, long way away.